Hey guys, we're going to learn how to graph logs and exponential functions today. So I'm going to put my screen over here so that you can see that and zoom in a little bit. Okay, so when we talk about an exponential function, we are going to have a power that has a variable in it. So you're going to be looking for an x or another variable in the power, and that's how you'll know it's exponential, okay? So the parent function for exponential is going to be f of x equals b to the x. And we've been really careful about doing a capital B here because when we do our transformations, we want to remember that that b, the little b that's next to x, is a horizontal shrink or shift. This is not. This is just the base of the exponent. So capital B doesn't change. All it does is changes this original point that you have. So I want you to think about an exponential function like this, y equals 2 to the x. This is an exponential function because x is a power, okay? If I plug 0 in for x, I get 2 to the 0, right? So y equals 1. Anything to the 0 power is always 1. So see how it doesn't really matter what this capital B is. Anytime x is 0, y is always going to be 1. So that's why our original point is 0, 1. Okay? Then if we do the same thing and we did 2 to the negative 1, this will give us 2 to the negative 1 is 1 over 2, so 1/2. So if x is negative 1, then y is going to be 1 over b. In this case, b was 2. And then if I plug a 1 in, then I have the big B to the 1 power, and we just get 2. So when you plug a 1 in, you just get the base. So these are the original points for an exponential graph with a base of big B, okay? So we've got negative 1 over, and negative 1 and 1 over b. So negative 1 and 1 over b is right here. So what I want you to think about is that it doesn't matter what negative number I put into this equation. I'm just going to get 1 over 2 cubed, or 1 over 2 to the 4th, or 1 over 2 to the 5th, okay? So we're just going to get a smaller and smaller and smaller number, and this is going to approach a number. It's always going to approach whatever that vertical shift is. So if there's not one, if I have like a plus 0 right here, then that's going to approach 0. Okay, we call this k in our function, if you remember, so k. So the horizontal asymptote is going to be whatever this vertical shift is in the function. For the parent function, it's going to be 0. So we're going to have a horizontal asymptote right here at 0, okay? And remember, this is an asymptote. So the graph is going to get closer and closer and closer to it, but it's never going to touch it. And so that's why we call it an asymptote, because we don't touch it, okay? So it's just a line that the graph is approaching but never touches. And when you look at it in the computer, the pixels can't tell the difference between these two. And so it's going to get closer and closer, and it might look like it keeps going, or it will actually stop graphing it because it knows it can't graph that, it can't touch that point, and the pixels are so close together it can't graph anymore. So it's never going to show you that whole graph, but this graph will go on and on forever right next to that asymptote. So when we look at the domain, we're talking about the left to the right. This is going to go like this, and then this is going to go like this forever, and the domain is negative infinity to positive infinity, okay? So any exponential graph, the domain is negative infinity to positive infinity, okay? And then the range is wherever that asymptote is, so it starts at the asymptote, and then this one's going to go up to infinity, okay? Now remember, it does not touch the asymptote, so I have to use a parenthesis. The asymptote always uses a parenthesis, so we're going to do a parenthesis here. Then we're going to write the horizontal asymptote is y equals 0. Another way you could say this is it's y equals k. Okay? And then the intercept is going to be whatever you have over here, 0, 1. The end behavior is going to be on the right. It's going to go to infinity. So on the right, it's going up. And on the left, it's not going anywhere. It's trying to get to this line, but it can't cross it. So that's 0, right? So on the left side of the graph, it's just going to 0. And so this is always going to be the horizontal asymptote. Okay? So we have our parent functions, we have our asymptote, and then we graph it. It starts really close to the asymptote, it touches that point where 0 is, and then it's going to veer off quick. All right, so that is our exponential graph. Now, we can use the function transformations that we've been learning on our, we just barely did it in our graphing unit for trig, on this graph, on any graph as well, to be able to graph it. Okay, so I put a reminder right here in your notes about what each of those things will do to the original points of the graph. Now, it will also, right here where this says a vertical shift, you're going to add or subtract from the y values, and the asymptote is a y value, so this includes the asymptote. Okay, so if I have a k value that's -2 and my original asymptote started off at 0, then now my asymptote is going to go down 2, and my asymptote is going to be 0 minus 2, which is -2. So the asymptote would be y equals -2. This is your standard form of an exponential function. Okay, so y equals a, this is your vertical stretch or shrink. Capital B is the base of the exponent. Little b is going to be your horizontal stretch or shrink. X minus k is left or right. And then plus k is your vertical shift up or down. Okay. Remember, when it's next to x, it's always opposite. So these guys, the b and the h, are going to be opposite of what you think. But a and k are going to do what we think they're going to do. All right. Okay, let's do an example. So we're going to start off with 3 to the x minus 2 plus 1. The first thing I want to identify is what is big B, okay? So am I always going to look at this and I'm going to say, does this 3 have a power right next to it? It does. So 3 is my big B. So big B is 3, okay? So down here in my chart, we know that big B, so we're going to do -1, 0, and 1, okay? And we know that this is 1 over B, so 1 over 3. This is 0, 1, always, and then this is 1, and then B, so 3. Okay, so these are my starting points. Now the domain, this is an exponential. Okay, so anytime it's exponential, it's going to have a horizontal asymptote, and it's going to have a domain of -infinity to +infinity. This asymptote is y equals, so it's going to be a horizontal line, and it's always going to be that vertical shift. So if I look right here, put a little HA under that, that's going to be your asymptote is 1. Okay, so we will do some little bit of math right here. So let's say our normal asymptote was 0, and we know I'm moving the graph up 1 because that's what k is. So I add 1 to y. So we're adding 1 and we get y equals 1. So that's how you do the math for it, but really it is just this number at the end. This 1 is your asymptote. So the first thing I want you to draw is that asymptote. So here's 1. Okay, so I'm going to draw an asymptote like this. So now my graph is either going to be all above that asymptote, either direction, or it's all below the asymptote, depending on the reflections that I have, okay? So the range is either going to be -infinity up to 1 with a parenthesis, or it's going to be 1 with a parenthesis to infinity. All right, so we have to actually get a graph going to figure that out. Okay, remember the 3 is not a transformation. So we have this x minus 2. And we're going to identify, did that move the graph to the right or the left? So you have to write either right or left. This one is going to be right, which means I'm going to add 2 to the x value. Okay, so I'm going to take each x value and I'm going to add 2. So positive 2 minus 1 is 1. Add 2 to 0, add 2 to 1, and you get 3. Okay, and then the other transformation is this 1. So this is going to be up. So you either have to write up or down. So up 1, and that means add 1 to y. Okay, so I'm adding 1 to 1/3, and some of you use a calculator and some of you don't, and that's fine. So 1 plus 1/3, and it's 1.33. So you could write 1.33, or you can write 4/3. Okay. And then I add 1 to this, and we get 2. And we add 1 to this, and we get 4. So these are our points: 1 and 4/3, 2, 2, and 3, 4. We always have to have those exact 3 points on the graph. So I'm going to start here. I'm going to start here at 1 over 1 and up 4/3. So 1 and just a little bit more is going to be right there. Okay. And then we're going to do 2, 2. So over 2, up 2. And over 3, up 4. Okay. So that's going to be the graph. So I'm going to say this didn't reflect at all. So it's going to start here next to the asymptote. It's going to be really small like this. And then it's going to go up like that. So once we have the graph, we're going to put that into our range. And then notice that this is the line 1. And the graph is all above that. So parenthesis 1 to infinity. And I want you to say, did I remember to use a parenthesis? Okay, do that for a little bit so you can make sure that you put a little check by that yes, I did a parenthesis, because I don't want to miss it because of that. All right, and one thing that we don't have on these notes is the end behavior, but I want to write that on here, okay? So the limit as x approaches negative infinity, that's the left side. And on the left, this graph is going to the asymptote, which is 1. Okay, so if I notice on the left, this graph is never going to hit 1, but it's going to be really, really close. And then on the right, as x approaches infinity, the graph is getting bigger and bigger.
All students that are attending the cultural diversity meeting, please meet in the alumni room, please.
Okay, so that is graphing an exponential function.
Please head towards the alumni room.
Now we're going to switch gears and we're going to do graphing of the log. So you can't see this very well, so I'm going to write it so you can see it a little bit better. But this is what that log looks like. It has a little b, capital B down here, which means the base. Okay, so this is the base of the log, and that's how our ordered pairs are going to go. All right, so you notice at the top of your page, it says exponential and log functions are inverses of each other. That means the x and y switch places. So if we look at our exponential graph that went 0 and then 1, this one's going to switch and do 1 and then 0. Capital B and 1, 1 over b and negative 1. Okay. Now the log graph, because the exponential graph had an asymptote that went this direction, the log graph has one that's vertical. Okay. And the vertical asymptote is going to be however you move your x value. So the vertical asymptote changes with x. So whatever's in the parentheses, that's the way that the asymptote is going to move. Okay, so it's the horizontal shift. And then remember again, big B is the base. It's not a horizontal shrink or stretch. It's just the base for the starting point. Okay, and just like the ordered pairs switch places, so do domain and range. So this has a domain of 0 to infinity and a range of negative infinity to infinity. So it's exactly the same as the exponential, it's just switched places. The vertical asymptote is x equals 0. So not horizontal now, it's vertical. Sometimes I remember it because the word log has this L right here, and that's the same shape as the asymptote. Okay, so vertical asymptote. The intercept is going to be an x-intercept. That's always going to be at 1, 0, unless you shift to the left or the right, and that will change according to that x value, which is the x minus h. Okay. The end behavior on the right side is going to infinity. So that's kind of the same as what we were looking at. The left side is a little bit different because we have an asymptote. So x is approaching 0 on the right side of the asymptote, and the graph is going down. So that's how we write the end behavior on that. Okay. Two little notes here is that two common logs that you'll see are just a normal log like this, and this will have a base 10. So if there's not a log, if it looks like this, then the 10 is the base. Okay. And then we have a natural log, which is a log base e. So anytime we have a log with a base of e, we change that around and we call it a natural log of x so that we don't see the base. Okay. On your calculator, it looks just like this, and it's ln. It's not in, it's ln, natural log. They did the words backwards. I don't know why. Okay. So, and then this is our parent function for the log graph. And all of the transformations are exactly the same. We're doing the same exact thing. So let's do it for this graph. Okay. So now remember that we're switching the x and the y. Okay. So this is going to be 1, 0, and then 1 over b. So let's write down what b is. So b is the base here. We actually have, this should be example 2 right here. So example 3, sorry. So right here, this is our base, this 2. So that big B is a 2. So when I do this, I'm going to have 1/2 is my 1 over B. And that's where negative 1 is going to be. And then we have 1. And then we have 2. Okay. So it's always 1/2, 1, and 2 because the base was 2. Remember, on a log graph, the range is negative infinity to positive infinity. And the asymptote is vertical. Okay, so to get the asymptote, I look at the parentheses. I have x plus 7. I'm going to set that equal to 0. And you get negative 7, which is going to be the same as if I did x equals 0 and it shifted to the left 7. So 0 minus 7 equals negative 7. So the vertical asymptote is negative 7. So over here on the graph, I'm going to go to negative 7 and draw that vertical asymptote. Okay. All right, let's look at the transformations. So we look right here, we've got this x plus 7. This means I'm moving left 7. So on my transformation, I'm writing left 7. And that means subtract 7 from x. Okay, and then we have a minus 3, so down 3. And that means subtract 3 from y. So I'm going to subtract 7 from x, so minus 7, minus 7, minus 7, and I'm going to subtract 3 from y.
Susan, your dad is here to pick you up at student parking. Susan, your dad is here to pick you up by student parking.
Okay, so we come up with our ordered pairs. So negative 6.5, negative 4, negative 6, negative 3, negative 5, negative 2. So I'm going to mark those. So negative 6.5 and negative 4 is 1, 2, 3, 4 right here. And then negative 6, 3 is right here. And then negative 5, negative 2 is right here. So we have these 3 points. So remember that logs, they look like an upside down L. It's going to be, it goes up and then over like this. So it's going to be next to the asymptote. It's hugging the asymptote. And then it hits that point and then it will veer over. Okay, and you cannot put this in your calculator, okay? Because your calculator automatically uses a 10. So if it's log base 2, then this is no calc. I can't put it in the calculator, okay? And honestly, when you look at a log in a calculator, it looks weird and you'll draw it wrong because it looks like it stops. You can't see the tail come down. Okay, so now looking at this on the domain, I noticed that the graph, instead of going from 0 to the right, it goes from negative 7 to the right. But negative 7 is an asymptote, so I use a parenthesis, and we do negative 7 to infinity. Okay, and then let's talk about the end behavior. So we have the limit as x approaches infinity. So this is the right side. It's going up forever to infinity. Okay, and then the limit as this one is going to negative 7. Okay, so it's negative 7. And then I look at negative 7 and I say, is my graph over here? Okay, so this is the left side of negative 7. Or is it over here on the right side of negative 7? So because it's on the right side, I put a plus sign right here, which means from the right. Okay, so negative 7 from the right, then this graph is going down. As I get closer, I'm on the right side of the graph, and as I get closer and closer and closer to the asymptote, my point is going down. Okay, the y value is decreasing. All right, then we have our example that I kind of started, example 2, so you'll have to turn your page back. This is going to be, so we want to identify, is it exponential or is it log? Okay, because depending on what it is, that's going to determine what value you're using to start with. So this is exponential, so I'm going to have a 0 and a 1. Okay, so 0 and 1 is my starting point, negative 1, and then 1 over b. So in this case, b is 2, so 1/2. And then negative 1, 0, and positive 1 and b. Okay, domain on exponential is negative infinity to positive infinity. The asymptote is horizontal. My k value is negative 2. Okay, so go to negative 2, draw your asymptote, and we've got that. All right, now we're going to look at our transformations. So I noticed that a is negative 1. Okay, this is like having a negative 1 times 2 to the x plus 1. So negative 1 is a x-axis reflection. X-axis reflection, okay? Which means I multiply y by negative 1. In x-axis reflection, we multiply y by negative 1. All right, and then we have this little dude, the x plus 1. That is left 1, so I subtract 1 from the x value. And then I have a negative 2, so down 2, add 2 to the y value, okay? So x-axis reflection, I'm multiplying y by negative 1, so that gives me negative 1/2, and negative 1, and negative 2. And then from there, I'm also going down 2, so I'm subtracting 2. So this is going to be negative 2.5, negative 3, and negative 4. Okay? Then my x value, I'm subtracting 1 from x. So negative 1 minus 1 is negative 2. 0 minus 1 is negative 1, and then 0. So our points are negative 2 and negative 2.5, negative 1, negative 3, and 0, negative 4. So I want you to think about if I have a graph that looks like this, then I have a line like this, and I'm going to have an exponential graph looks like this originally, but we're reflecting it, so it's going to look like this. Okay, I'm flipping it over that axis. So that's where your point should kind of lead you. So negative 2 and then negative 2.5 is right here. Negative 1 and negative 3 is right here, and then 0, negative 4 is right here. Okay, so I noticed that this is going to come like that, and then this is going to go next to the asymptote like this. Okay, so we always want to kind of draw our graph, have an idea of what it's going to look like before you try to connect your dots, but you can get those in the right spot. From the graph, I can do the range. So looking at this graph, everything is below that line. So that means negative infinity up until the asymptote, which is negative 2. Remember your parenthesis. Okay? All right, let's look at the end behavior. So the limit as x approaches negative infinity. All right, so on the left side of the graph, it's still going to be next to the asymptote right here. Just because it's under it, it's still next to it. So negative 2. And the right side, now this is where it flipped, right? So instead of going up forever, it's coming down forever. So it's going to go to negative infinity, bigger and bigger and bigger. Okay? All right, our last two examples have to do with domain. There's an example here. So when you're doing domain of a log, you want to just circle whatever's in the parentheses. And sometimes it's just an x, okay? So whatever's in the parentheses, so this one's 4x plus 1, has to be positive, has to be greater than 0. So I'm going to subtract 1 and divide by 4, and we get x is greater than negative 1/4. Okay, so if it's greater than negative 1/4, then it's negative 1/4 with a parenthesis to infinity, and that would be the domain. Okay, parenthesis. Okay, all right, and then if I look at, and that's also going to be your asymptote. Okay, this one, 5 minus 3x is greater than 0. Minus 5, negative 3x is greater than negative 5. Divide by negative 3. X, when I divide by a negative, I have to flip the direction of the inequality to less than. And negative divided by negative is a positive. So x is less than 5/3, which means negative infinity to 5/3 parenthesis. Okay? And that's how you do domain for logs. All right, you guys, let me know if you have